Hello everyone. As you all know, we have started with the gas laws. We have first completed the first gas law, that was Boyle's law. Boyle's law was what? It was when pressure is inversely proportional to volume at constant temperature. The second law that we studied was Charles' law. When I say Charles' law, it was volume is directly proportional to temperature at constant pressure and number of moles. So today what we are going to study is the remaining two gas laws. One is GAY Lussac's law and second is Avogadro's law. Starting with GAY Lussac's law, you can see very first over here, when we talk about Gay Lussac's law, you can see we have four variables over here: pressure, temperature, volume, and mass. And if I take any of the two variable, you can see I have taken pressure and temperature as variables, and volume and number of molecules will remain constant. So if pressure and temperature is taken to be variable, that law will be termed as Gay Lussac's law. You can see the very first point. I have taken a gas cylinder containing gas molecules, and you can see we have kept over it a piston. And when I said piston, above that piston I have kept some weight in the form of pressure. When I say I have kept some weight in the form of pressure, because I don't want my volume to expand, because I want my volume to be constant. So you can see over here, when you heat the molecules, as you know, when you heat it up, the molecules, they are going to increase their kinetic energy. As the molecules are heated, their kinetic energy increases, and as the kinetic energy increases, it start colliding with each other. When they start colliding with each other, they'll hit the walls of the container, and because they cannot expand, what happens over here is they are going to increase their pressure. So over here you can see what happens. We are keeping more and more weight, so the pressure increases and the volume remains same. So what we say is, as you increase the temperature, the pressure goes on increasing, because the molecules are hitting the container with greater force. From this we can conclude that pressure is directly proportional to temperature, keeping what constant? Volume constant. So what will be your Gay-Lussac's law? We say Gay-Lussac's law is what? At constant volume, pressure of a given mass of gas is directly proportional to temperature. And if I want to write it in mathematical terms, it will be pressure is directly proportional to T, temperature, at constant V and N. We can write it as P is equals to K into T. That will be P upon T is equals to K. As you can see, K is nothing but my proportionality constant. So hence, we from this what you get is P1 upon T1 is equals to P2 upon T2 is equals to P3 upon T3. So if you have a question in exam for Gay Lussac's law, what you need to do, you need to write down the statement that will carry 1 mark, and the explanation will carry 1 mark. So we can have this question for maximum 2 marks. Next, as we move ahead with graphical representation of Gay Lussac's law, you can see how are we going to represent the how are we going to represent Gay Lussac's law. First of all, as you can see, pressure is directly proportional to temperature. Means if you increase the pressure, temperature will increase. So when I say pressure is increasing, temperature is increasing, what happens? We know you'll get a graph which will be increasing. I can say it will be a straight line passing through origin. You can see if pressure is increasing, temperature is increasing, means if the temperature is high, pressure is high, the point that will lead is this one. Now if I say my temperature is decreased, my pressure is also decreased. So the point that you get is this way. In this way, when you plot the graph, I'll get a straight line, and if we extrapolate it, we can extrapolate to the origin. So what we get is a graph that will be a straight line. When I say graph will be a straight line, you can see over here, as we are saying, the volume is constant. If you remember, when the temperature was constant, it was isotherm. When the pressure was constant, it was isobaric. When I say volume is constant, it's called as isochoric. So whenever in a process, when the volume is constant, we call it as isochoric. So this is what we have studied for the graph of Gay Lussac's law. So let's see some numericals over here on the basis of Gay Lussac's law. As you remember, the formula was P1 upon T1 is equals to P2 upon T2. You can see we have a question. A glass container is sealed with gas at 0.800 atm pressure, and 20 and at 25 degrees Celsius. The glass container sustains pressure of 2 atm. Calculate the temperature in degrees Celsius which gas to which the gas can be heated before bursting the container. As you can see, sabse pehle what they have mentioned, they have a glass container which is sealed. When they say it is sealed, means the volume is constant. It cannot expand. And it has at a pressure of 0.8 when the temperature is 25 degrees Celsius. They have said the glass can sustain a pressure up to 2 atm. The maximum pressure that the glass container can sustain is 2 atm. So we need to find out till what temperature can we heat the glass before it bursts. So over here, as we can see, the given condition P1, that is 0.8 atm. The temperature that we have is T1, 25 degrees Celsius. And as you know, when we are solving numericals, every time you need to convert degree Celsius into Kelvin. Even if they're asking you to find the answer in degree Celsius, you need to convert degree Celsius into Kelvin. So 25 degrees Celsius will be converted into Kelvin when you add 273. So it becomes 298 Kelvin. T2 is equal to 2 atm. We need to find the temperature in degrees Celsius. So as we know, we have the formula from which law? GAY Lussac's law, because container is sealed. Container is sealed means the volume is constant, and therefore we'll apply GAY Lussac's law formula P1 upon T1 is equals to P2 upon T2. So when you solve this, you can see P2 will be what? P1 into T2 upon T1. When I say P1 into T2 upon T1, P1 was what? 0.800. You can ignore that 00. T2 was 298 Kelvin. Sorry, T1 was 298 Kelvin, and T2, something that we need to find, sorry, and P2 is equal to 2 atm. So P1 is 0.8, P2 is 0. P2 is 2. When you substitute the values, you can see 2 divide by 0.4, then you can see 2980 by 4. When you divide, the answer is 745 Kelvin. But they have told you to find the answer in degree Celsius. So what we are going to do is the answer that you have got in Kelvin, we are going to convert it into degree Celsius. Just minus it by 273. So when you minus, you get the answer as 472 degrees Celsius. The temperature to which the gas container can be heated up is 472 degrees Celsius. After that, it will burst. So this is the maximum temperature to which it can be heated up. Next question we have, second one. A tungsten filament electricity bulb is filled with gas at 1.2 atm pressure at 18 degrees Celsius. A thin glass light bulb can sustain a pressure of gas up to 1.5 atm. Calculate the maximum temperature up to which the light bulb can sustain heat. Almost a similar type of question. You can see we have a tungsten filament bulb which has a pressure of 1.2 atm at 18 degrees Celsius. And it can sustain a pressure of up to 1.5 atm. We need to find the maximum temperature up to which the bulb can sustain the heat. So again, if I say P1, I have P1 is equals to 1.2 atm. Then temperature T1 is equals to 18 degrees Celsius, which I have to do 18 plus 273, which is equal to 291 Kelvin. Next, I have P2, which is equal to 1.5 atm. We need to find T2. It's almost a similar sum. We know the formula, as they have said about a bulb. You know, bulb cannot expand, the volume will remain constant. We have the formula P1 upon T1 is equals to P2 upon T2. You need to solve this formula on your own. I'm not solving it further. It's P2. Sorry, if you have to find T2, it will be P2 into T1 upon P1. We know P2 is 1.5, T1 is 291 upon 1.2. So you can solve this question on your own. Moving to the next question that you need to solve. Again, this will be done by you. A gas has a pressure of 699 mm of Hg at 40 degrees Celsius. What is the temperature at standard pressure? Means you can see the gas has a pressure of 699 mm of Hg at 40 degrees Celsius. They have asked what will be the temperature at standard pressure. If you remember, when we studied measurable properties of gases, at that time I had told you what are the standard values of pressure. So you can see we have 1 atm, which can be approximately equal to 1 bar, or you can say 1.01 into 10 raised to 5 Pascal, or you can say 760 mm of Hg, which is equal to 760 torr, or 76 centimeter of Hg. These are all nothing but standard values of pressure. So as you can see in the given, we have 69 mm of Hg. So the standard pressure that I'll take is what? 760 mm of Hg. So from this, sorry, from this, what you can see is I have P1, that is 69 mm of Hg, P2 is 760 mm of Hg, T1 is 40 degrees Celsius, which I need to convert into Kelvin. So 40 degree plus 273, you will solve and you will get the answer. So from this, you have to find what? Temperature. Means again, you have P1, P2, T1. You need to find this T2. I think you'll be able to do this question. So I'm not solving this question further. You can do this. And you just need to note down over here, when you are taking these values like P1, P2, T1, T2, you should always keep the units to be same. But an important point to note down is that you cannot keep the temperature units always. If you think that degree Celsius will get cancelled, no. Please convert degree Celsius to Kelvin. That is very important. Otherwise, your answer will be wrong. As we have completed GAY Lussac's law, we'll move to the next very important law, that is Avogadro's law. Now, when we talk about Avogadro's law, we have studied already three laws and their variables. Like the first one that we studied was Boyle's law, in that the variables were pressure and volume, correct? And the constant was temperature and number of moles. When we studied Charles' law, it was having variables like volume and temperature, whereas the constants were pressure and number of moles. Now, when I say GAY Lussac's law, we saw pressure and temperature are variables. And what are constant now? Volume and number of moles. So what is left now? You can see the next term when we talk about Avogadro's law, we are going to have volume and number of moles to be variable, whereas pressure and temperature will remain constant. Moving ahead with Avogadro's law, you can see, I'll give you a general example. Like if I bought a bottle of Pepsi from the market. Now, when I bought a bottle of Pepsi from the market, I bought like 1 liter Pepsi and 2 liter Pepsi. Now, when I say 1 liter of Pepsi and 2 liter of Pepsi, if I compare, you can see 1 liter will contain certain molecules and 2 liter will also contain certain molecules. Obviously, which bottle will have more number of molecules? Yes, the answer is 2 liter one, because it is more volume, more the number of molecules. Similarly, if I say I bought a bottle of Coca-Cola from the market, both the bottles which I bought were 3 liters. So if I say the volume is same, what about the number of particles? The number of particles will remain same. The number of molecules will be same. So here, as you can see, when I say 1 mole consists of this many particles. Now, when I say 100 mole, you can see the volume has increased. As the volume has increased, the number of moles will also increase, because 100 moles cannot be accommodated in such a small space. So we need to increase the volume. So what we say over here is, as volume increases, number of moles increases. So we say volume is directly proportional to number of moles at constant pressure and temperature. So we say over here, we can have 2 to 3 statements for Avogadro's law. Very first, as you can see, volume of a gas is directly proportional to number of moles of gas at constant pressure and temperature. Or you can say equal volumes of gases contain equal number of molecules. Equal volumes of gases contain equal number of molecules. So you can have 2 or 3 statements for Avogadro's law. You can write any one of them. Moving ahead, you can see one more as we have. It states that at constant temperature and pressure, equal volumes of gases contain equal number of molecules. You can learn any of the two above. As you can see, V is directly proportional to N. N is your number of molecules. V is volume. P is pressure and T is temperature. Moving ahead, as we talk about Avogadro's law, we have studied about Avogadro's number. You know, Avogadro's number will give you the number of particles. Particles can be atoms, molecules, ions, it can be compounds, it can be electrons, protons, neutrons per mole of a substance. Avogadro's number is equal to what? 6.022 into 10 raised to 23. And we normally represent Avogadro's number by the symbol Na. We say 1 mole of a gas contains Avogadro number of particles. When I say 1 mole of a gas contains Avogadro number of particles, means it contains 6.022 into 10 raised to 23. So similarly, if I say 1 mole of a gas at STP, because when we talk about Avogadro's law, its volume is directly proportional to number of molecules, we say 1 mole of a gas at STP is equals to 22.414 mole per liter, or you can say mole per dm cube. Means 22.414 moles are present for 1 liter, for 1 mole of a gas at STP. Similarly, we also refer to it as molar volume because we are talking in terms of 1 mole. So if I ask you the volume of a gas at STP, we say volume of a gas at STP is equals to N into 22.414 dm cube. So it's not mole per liter, it will be dm cube or liter, because 1 mole has 22.4. So how many moles are present in that much volume? We can find just multiplying by N. N is nothing but number of molecules. So I have a question over here. Calculate the volume in liters occupied by 7.40 gram of ammonia at STP. Molar mass of ammonia has been given as 17 gram per mole. So if I check, or if I go for the given condition, what do I have for given over here? You can see, first of all, we can write given, that is mass of ammonia NH3 is how much? It is equal to 7.40 gram. Similarly, I can say we have molar mass of ammonia, which is equal to 17 gram per mole. This is what you have in given. Yes. And what do we need to find? We need to find volume of ammonia gas at STP. So when I say volume of gas at STP, solution is what? We have the formula for volume of gas. We have the formula volume of gas at STP is equal to N into 22.414 liter, or I can say dm cube, anything you can write. So from this, if I have to solve this, we need to find what? We need to find N, that is number of moles. Now we know what's the formula for number of moles. Number of moles is equal to mass upon molar mass. Means I can simply say it is equal to 7.4 divided by 17. So when you solve this 7.4 divided by 17, what do you think the answer will be? So I can just calculate it. 7.4 divided by 17 gives me 0.435. We have got number of moles. So from this, if I have to calculate the final answer, that is volume of gas, as you know, the formula is N into 22.4. So we have N as 0.435 into 22.414. So the answer that you get after multiplying, so you can see this, if I multiply by 22.414, I get the answer as 9.75 liter, or if you want, you can write it as 9.75 dm cube. So this is a question which we have solved using Avogadro's law. So I think we have understood this question. You can write down the question and you can write down the solution, because the next question, similar type of question, I'm going to give you that question as homework. Hoping that you have done writing. We'll move to the next one. C. Calculate the volume in liters occupied by 49.8 gram of HCl gas at STP. If you see over here, we have the given as what? Mass of HCl gas, which is equal to how much? It is 49.8 gram. We have molar mass of HCl, as H is 1 and chlorine is 35.5. They have already given 36.5 gram per mole. What do we need to find? Same, volume of gas at STP. You know the formula for volume of gas at STP is equal to what? Yes, it can be same volume of gas at STP is equals to N into 22.414 liter. So we know N is what? Number of moles, which is equal to mass upon molar mass. That will be 49.8 divided by 36.5. And that will multiply by 22.414. So when you solve this, you'll get the answer for your Avogadro's law. So this is a question that you need to solve on your own. So as we can see, we have completed two laws, Avogadro's law, and the last one was, previous one was GAY Lussac's law. So till now we have studied four laws. The first one was Boyle's law. Second we had was GAY Lussac's law, Charles' law, and Avogadro's law. Next we have, you can see, is relationship between molar mass and density. Now when I say molar mass and density, you can see V is equals to K into N. As we know, according to Avogadro's law, V is directly proportional to N. When I say directly proportional, if you remove the sign, we get is V is equal to K into N. Now as we know, number of moles is equal to mass upon molar mass. So V is equals to K. Instead of N, we are going to put is small n, that is mass upon molar mass. Now we know M, if you rearrange, you can see we get as K into M upon V. Now mass upon volume, what is it? You know, mass upon volume is density. So I can say density is equals to mass upon volume. So instead of mass upon volume, I can write D. What I'll get is M is equals to K into D. Means if I say K is nothing but a proportionality constant, I can say M is equal to, or I can say M is directly proportional to D. Means when I talk about relationship between molar mass and density, we say they are directly proportional. These types of derivations are very important for entrance, because if they have just given you molar mass and density, you can relate them as if molar mass increases, density will increase. You can solve the formula as M1 upon D1 is equals to M2 upon D2. So as we have completed the four gas laws, first was Boyle's law. Pressure is inversely proportional to volume at constant temperature, keeping the mass of a gas to be constant. Second we did was Charles' law. Volume of a given mass of gas is directly proportional to absolute temperature at constant pressure. Then third we did was after Charles' law, it was GAY Lussac's law. Pressure of a given mass of gas is directly proportional to temperature at constant volume. And fourth we completed was Avogadro's law. That is, volume of a given mass of gas is directly proportional to number of molecules at constant temperature and pressure. Or you can have a statement that at constant temperature and pressure, equal volumes of gases contain equal number of molecules. So we have now studied four gas laws. You need to remember, when we talk about GAY Lussac's law, we have studied over here. We also have a law which is called as GAY Lussac's law of combining volume of gases. That is one law according to law of chemical combination that we mostly study in first chapter. So please don't get confused between both of them. GAY Lussac's law and GAY Lussac's law of combining volume of gases, they both are different laws. I hope you have understood all the gas laws. We'll meet in the next lecture to study about a very important equation which is called as ideal gas equation. I hope you have understood today's topic. Have a nice day, everyone.